I don't know if you can push it out. I have Amin Barkia. I don't know. Who are still speaking, and I think I don't know if I am the. Now it's in Monira Belmai. I have the sound from his mic. From his mic.
Who?
Who?
I don't know. Sometimes maybe I am connected from two meetings.
Maybe you are.
Yeah.
So maybe you are connected in two sessions.
Yeah. Please close the second one.
Okay.
And also try, please, to share your presentation with us.
So for this session, you have two chairs. Amin Berkia
Yeah.
and Professor Abdulkarim Hakik.
Okay. Okay, I am sharing my. I did not share my computer. Oh, where may I share my computer?
Yeah.
Please. Do you see my computer? No, I don't think so.
Not yet.
Not yet.
Yes.
And now?
No, not yet. Yeah. Yeah.
It is good?
Yes, very good.
Okay.
Go ahead, please.
Thanks.
Welcome.
Hello, everyone. I am Fabrice Nolak from University of Mons at Belgium. From now, I am truly honored to present to you my first conference speech as a part of my PhD program. My research work is about smart farming, focuses on data analysis. So we wanted to start our long research work with an appropriate architecture that meets the needs of farmers and current constraints of security, privacy, connectivity, and so on. That's why the title, Big Data Storage and Analysis for Smart Farming. Without further delay, let's start our presentation with our outline. First, we start with a brief introduction of big data, followed by a short presentation of different fields that constitute the main sector of smart farming. After that, we will take more time to present our architecture we realize as our contribution, and we will close this presentation with a resume. First, a big data. What can we say about a big data? Big data has major evolution in last years and impacted several sectors, among with smart farming, which is our concern. It is characterized by some keywords. From now, we count 10 keywords with velocity, variety, veracity, volume, venue as the 5 main characteristics, followed by validity, variability, vocabulary, vagueness, venue. This characteristic can be represented as the dimension of big data: storage, processing, and analytics, simplified in 3 keywords: volume, velocity, variety, and center on value, the data value. Big data is carried by the value chain: acquisition, analysis, curation, storage, and usage. All these center on data as big data. I will not take more time to present any change on the value chain because I think all of us can know this. So I will just go to the smart farming. Smart farming has 2 main sectors. SSA as smart sustainable livestock agriculture, and PLF for precision livestock farming. It fuels plants and animals. There are several factors that influence both sectors. Let's take a look on the PLF, precision livestock farming, the main concern. Livestock farming is carried out by these main fields: animal behavior, for the animal habits, genetic, genomic, and genetic diseases or irregularities. It extends species protection to eradicate species extension. Animal welfare is about animal health and nutrition for their diets. Others are not only influenced by PLF. Climate resilience, productivity, sustainability, human and stakeholder are shared between PLF and SSA. As our contribution, we will present the architecture we set up. Our architecture has three major layers. The first layer is acquisition. The second is processing and by storage. The third is visualization. So first thing first, data acquisition. We start by interviewing our data provider, also our partners of this project, on how we can get data to start development. We have many answers, many different answers. The first is, say, we have already a swap web services which can give you some data. So we can get data from REST or swap services, because the second one says we can develop or we can build up a REST services to provide you data you need. So our system can get data from web services, REST or swap web services. The third said we can give you data from by email, because they already have a system which can send email which attach file with some data. So we get data from SMTP server. The third, another said we can only send you a data by FTP, and we get each days a zip file on our FTP, and we can also connect it with MQTT broker to some sensor or stations to have weather update. Other data are collected in different formats: JSON, XML, CSV, XLS, etc. And we are using several. From now we have as data in our database, we have 22 farms, more than 10,000 animals in 15 species. And also a weather observation, we have 258 stations, more than 3 million of data between 2008 from 2020 from the current year. All data we use to collect that data, we use several connection protocol, and especially EMQX broker to connect with our sensor and other stations. Second, data processing. As the entry point, we have Apache Kafka. And we have in Apache Kafka, we make many producers, as we have a data provider, and our processing engine is some Python script. We have two-way, the real-time way for real-time data and batch way for historical data. Data are stored into Cassandra for NoSQL, PostgreSQL for SQL data. After that, we can visualize data with a front end built in Node.js for management, reporting, and to have a weather observation history. We also have a backend with Python, and we also build a GraphQL API. After that, we Dockerize all that. The the two last layers to have a cloud architecture. To simplify our architecture, we can see here at the right all our sources and MQTT for EMQX broker to connect with our sensor only. Apache Kafka, which we see as a orchestra, which redirect data from the batch line or the real-time line, and we store into Apache Cassandra or PostgreSQL. After that, we can visualize data, or either they are historical or they are real-time data. As a resume, we can say that we have a cloud architecture, stable and scalable for all type of farm, small, medium, or large farm. That architecture can store structure or unstructured data, and it is managed with a responsive web app. As a future task, we can see for more data sources, apply more data sources in our architecture. We can build up a knowledge discovery to exploit to valorize more our data, and at the end we can build up a decision support system for farmers. I have some demonstration if I can. Yeah.
How long is the demonstration?
2 or 3 minutes.
2 or 3 minutes?
Yeah.
I think Professor Haqiqi, he has time for 2 minutes. Okay.
I can.
Yeah. Okay, Fabrice, okay. You have 2 minutes for your demo.
Thanks. Do you see my screen?
Yeah, we can see it.
From here, we have a real-time data for a dashboard for real-time data. But from now, we are not connected with any sensor, so we don't have some data. But here we have some apps stored in our system, maps, weather observation, another weather observation, and possibly our personal apps for collecting data from anywhere. So, for example, for weather from PalmSnap, we have many data, temperature, precipitation, humidity, and wind speed. This is all our stations. From here, we have all our stations, and you can change stations. From here, we can locate any stations we have in our database and also have some precision about that with and also the same information we have in other tab. From here, we cumulate that tab in daily, and here we have historical data. Also, we can have a real-time weather with open weather map. For example, from now at month, we have 7 degrees. And we also build up a personal application which takes 3 parameters and return a specific information, as we can see. We can administrate all that. For example, all our Python script, as I say in my presentation, we can schedule it here. For example, we have some scheduled tasks. We take data from Away, Sierra, PalmSnap, SRC, and Ori Automate. This one, the Ori Automate is sending back via FTP. So we can have here a last execution of the scheduled task, as we can see in the hour here. We can manage this. For example, if we want to disable one, or we want to enable one. For example, I will disable the last one, test 2. As an administrator, I can do it. I can do that, and we see that here test 2 is enabled. We can see the last execution of test 2, the 17th of this month. So I can disable it also. For access token authorization users, as an administrator, I can do all of this. And from here, I have some applications. As we see previously, testable personal application, administrator can also disable it or enable it. It can edit it. For edition, it can give another name, another icon, etc. Phenoble, which is not already enabled. We can enable it, and we will see it on our apps. That's all for this part. So thanks for listening. And from now, I am ready for any questions.
Thank you, Fabrice. So we have only one question in the chat. You can see it, Fabrice?
Discussion, that's one.
Yeah.
Conversation. Okay.
Please read the question and try to answer.
Okay. First, I will thank the speaker for the presentation. My question is about system use in acceleration of data processing in your cloud architecture of smart farming, such as heterogeneous system, CPU, FPGA. My question is about the system used in acceleration of data processing in your cloud architecture of smart farming, such as heterogeneous system, CPU, FPGA. As accelerator system, we didn't use any, how can I say it? We use a GPU cloud system because we choose all tools we choose to use a, how can I say, a free tools to build our architecture, to be more scalable, around the data, around the type of data and the velocity of data, because we think data are coming from many sources, and we have to be more modular to receive and store that data. So as accelerator system, acceleration system. No, we didn't use any acceleration system from now, because we are still on development, and the architecture are still on development.
Okay, thank you, Fabrice. One more question.
Yeah.
So if I understood well, in your presentation, you told more about an API that you developed.
Yeah, GraphQL.
Yeah. What you present is more a connected farming, is not smart. I didn't see the aspect of smart.
The API we developed, the GraphQL API, is just to expose our data without. If I can present you, it is this one. We just use it to expose our data with.
But you told about smart. Where is the smart part of your farm?
The smart part of my farm.
Yeah. Is a connected farm, is not a smart farm. I didn't see the smart part.
Ah, okay, connected farm.
Yeah.
Yes, because we are not a farmers. We are not, we as I say humans, if I can, are not the farmers. Humans are the developer of the system which will be connected with farmers and farms.
Okay, so you
So
agree
that
with me? It's a connected farm. It's not a
Yeah,
smart farm.
we are using this we are using our system to connect with farms, and the system we develop is for the smart farming. So the farms are already have connectors and sensor on animals, or the farm already have some tools which can provide us some data. So that farm are already connected, but they cannot manage their data. They cannot value their data. We provide them a tools to value their data. Thank you for your presentation. I would like to ask you about the technology you use for data visualization with Python and JS. Also, why didn't you use Cassandra? Is it a data type constraint? I don't know if I have a time to answer the last question.
Yeah, Fabrice, we can give you more time to answer.
To visualize our data, we use a JavaScript library, because our front end is built up with JavaScript with JS. We use Chart.js for graph and charts, and the others we use for Python. We only use Python to have a background, as I said, a daemon tools to be executed in background. So as example, when we want to collect our data from our emails, we use a Python script. When we want to take all data in our FTP server, we use a Python script. But for visualization, we use JavaScript library. We use for charts, we use Chart.js. We use OpenWizardMap for maps, and also Google API, Google Maps API. Also, why did you use Cassandra? We use Cassandra for NoSQL data because it is more, how can I say, more easy to take in on hand. So we want a tools which is, our first criteria is open source tools we want to use to be more scalable. That is not really a constraint for us, but we choose Cassandra for more than others, and because it is also a column-oriented column.
Thank you again, Fabrice.
Thanks.
I think now we can move to the second presentation.
Okay.
Abdelkarim, your mic, please. Abdelkarim, we can.
Sorry. Thanks, Fabrice. I have a last question before moving to the second presentation. Why you didn't use some machine approach for the processing of your data?
But first, because we want to, how can I say it? We want a application that farmers can take it easily. First of all, and second of all, a simple application that can be hosted without a lot of infrastructure, resources, and others. We want a simple app, simple for hosted, and simple for usage. because we think we are not, our application will not be used by a performance, but people which have a good knowledge in IT, for example. They are farmers, they want to focus on their main activity, so that we choose a simple things, a simple way. If I can say it like that.
Okay, okay. Thank you so much, Fabrice. We move to the second presentation. I don't know if the presenter is here or not.
Yes, I'm here, Mr. Chair. If,
you are Ismail Angry?
Yes, yes, I'm smiling.
Yeah, yeah, you have the floor, please. You have 15 minutes. Go ahead, please.
Okay, thank you, Mr. Chair. Could you please confirm that you see my screen?
It's okay. You can see your screen.
Okay, thank you, Mr. Chair. Dear chairs, dear participants, good morning, good afternoon to all of you. My name is Ismail Angri, and on behalf of my co-authors, Mr. Najid Abdullah and Mr. Mahfoud Mohammed, we'll present this work for the Cloudtech 20 conference. Our work entitled Performance Evaluation of Newly Implemented Resource Block Allocation Schemes on in-stray simulator for MMTC 5G Neo Radio femtocells. So the plan of our work is shown on screen. We'll make small introduction to the evolution towards 5G technology. We'll present architecture and use cases of 5G networks. Then we will talk about the radio resource management in 5G systems before presenting the different scheduling algorithms for 5G networks. The work contribution, and then before concluding, we'll present simulation results and discussions. So as we know, the millimeter wave bands offer new opportunities to 5G technology. The radio resource management, RRM, is the procedure of distributing available radio resources amongst users connected to the mobile network. The new 5G technology needs an efficient RRM. That's why in our work we have developed in C++ and simulate the scheduling algorithms already tested in 4G to analyze their behavior in a 5G MMTC environment. First of all, we'll present the different steps before arriving at 5G. So after the first generation, which was analog system, the second generation 2G, called the GSM for Global System Mobile Communication, is the first digital system, which is a packet switching mode where resources are allocated for the duration of the conversation. The capacity limitation of 2G led to the introduction of the third generation 3G, which uses a 5 megahertz channel to achieve a throughput of about 2 megabits per second. Then the fourth generation, or LTE for long-term evolution, which is a standard developed by the 3GPP project as part of the IMT Advanced Initiative. 4G allows a remarkable increase in throughput up to 100 megabits per second in downlink and 50 megabits per second in uplink, in addition to very low latency and a scalable bandwidth, which is up to 20 megahertz. The next is fifth generation, new telecommunication network, 5G, also called 5G in R, as a reference to new radio, which represents the new generation of the radio part of the technology, or also IMT 2020, which is new version of international mobile telecommunication IMT, intended to be operational in 2020, but this deadline has been postponed due to COVID-19. One of the strengths of 5G is that it's not limited to mobile broadband. In fact, IMT 2020 supports 3 use cases as shown in slide for the MMBB use cases, and with a flexible bandwidth up to 1 gigahertz, the peak data rate could reach 20 gigabits per second. MMTC scenario allows then a dense network with 1 million devices per square kilometer. The third scenario is UR-LLC, where the system latency presents a minimum of 1 millisecond. Sorry. Here are presented different bands dedicated to be used for the implementation of 5G network. First, the below 2 GHz band, which offers a large coverage. C band, which offers a compromise between coverage and capacity. And the third band is the high frequency above 6 GHz, which also called millimeter wave band, which currently presents a great opportunity for 5G. That's why in our work we have chosen to inspect the behavior of our model in a millimeter wave band environment. As in LTE, an NR frame with a duration of 10 milliseconds contains 10 subframes. A subframe length is depending on the size of slot, and an NR slot is made up of 14 OFDM samples. NR uses scalable numerology, which represents the physical transmission parameters in NR, such as subcarrier spacing, SCS. As consequence, NR supports multiple numerology, of which there is a multiple resource grades. In NR, we define the resource grid with the dimension of the number of subcarrier per resource block and the number of sample per subframe. And resource block in NR is defined as 20 consecutive subcarrier in the frequency domain. The resource element is the smallest unit of the resource grid to assign to different user. In our radio resource management has made several improvements over the old version used in LTE. The scheduling of the radio resources is made by what we call scheduler, presented in this slide, for downlink and for uplink. Each user calculates and establishes the CQI report, channel quality indicator report. This report will then be transmitted to the node B. Each TTI scheduler informs the user equipment of the resource allocation decision concerning the next TTI, as well as the best MCS or modulation coding schemes to use. At each TTI, the resources are allocated to different users based on the method used by the scheduling algorithms. So right now I will present the different scheduling algorithms used by 4G technology that we have implemented to be exploited by the G-Node B 5G base station during the resource allocation for downlink scheduling. The first one is the proportional field algorithms, PF. The approach applied by this scheme is based on the reconsideration of the average data rates of the path transmission. So the metric of this scheme is calculated by dividing the current transmission rate over the average path data rate. The next algorithm is max weight scheme, where the decision made is based on the packet delay criterion with the aim of maximizing throughput of the system for time-sensitive flows. To calculate its metric, we introduce the head-of-line packet delay, as presented in the chart and slide. DHOL characterize each packet and represents the time between its arrival and its successful transmission. Let's move to the exponential PF scheme, which is a metric, its metric is calculated following steps in slide, given the criticality of resource of real-time flows compared to non-real-time flows. Exponential PF was introduced to promote real-time traffic. Depending on the type of the packet, real-time or non-real-time, the method is different. For example, for non-real-time traffic, the metric is almost like the PF algorithm metric. For real-time traffic, and considering the packet delay threshold of each real-time flow at the time of scheduling and the maximum probability that the time of the first packet in the head-of-line queue exceeds the maximum delay, the metric uses then an exponential function, taking into consideration the number of real-time packets. The next and last scheme is the exponential rule algorithm. The main objective of the exponential rule scheme is to provide quality of service requirement by ensuring a compromise between optimization of throughput, fairness, and also the delay. Its metric uses also an exponential function applied to the DHOL delay, the maximum delay and the maximum probability of exceeding the threshold time divided by the square root of DHOL. In our work, we tested scheduling algorithms presented before, which have been applied to 4G in the objective to validate that they are also efficient and can be used in 5G network. To test our model, we use NS3 simulator tool. which is a discrete event network simulator composed of several models allowing simulation of different systems and network. The heart of the NS3 simulator supports multiple models. That's why the NS3 tool was chosen for the test and analysis of 5G networks, thanks to the new proposed and recently integrated model called millimeter wave model, allowing the design and exploitation of simulation of 5G networks, of course, in the millimeter wave band. So our scenario in a 5G network with the G-Node base stations and a number of 100 connected devices to simulate the MMTC scenario in a dense area. Simulation were launched for 3 types of flow, BC4, voice over IP, and video. The performance of 4 scaling algorithms was analyzed based on 2 parameters, namely system throughput and SINR, signal to interference plus nosage. So in this slide, variation of system throughput for the different algorithms is displayed. For BC4 flows, exponential rule offers the highest throughput as it has reached 2.3 gigabit per second, followed by exponential PF and then max weight. Also, the system throughput is also stable for all algorithms except exponential PF. The system throughput for voice over IP flows is shown here. In this case, for real-time flows, exponential rule scaling strategy allows a huge improvement in system throughput, being the only algorithm to exceed 2.5 gigabit per second per 100 user equipment for voice over IP, while 3 other algorithms, PF, exponential PF, and max weight, have almost the same behavior. In this slide, the throughput values for video over 5G are presented for the 4 schemes. The results showed that the exponential rule algorithm provides the best values up to 3.12 gigabit per second for video over 5G for system throughput. On the other hand, max weight has the worst performances, while PF and exponential PF have reached throughputs between 2.8 and 3 gigabits per second. So now we will discuss the SINR numerical results in a dense environment. We will start with the first type, which is the best effort flows. As can be seen in the SINR gradually decreases as the user equipment moves away from the base station for the different algorithms. The trajectory of the electromagnetic waves, as well as the propagation obstacles, explain the reached values. Specifically, the exponential rule has achieved values above 35 dB, while the 3 algorithms, PF, exponential PF, max weight, have almost reached the same values. The next slide is about SINR values for voice over IP flows. We can observe that, and as it was the case for BC4s, the decrease of SINR as the user equipment moves away the base stations. Exponential rule presents the peak of the SINR with 52.5 dB when we are close to G-Node B, 20 meters. For the maximum distance of 60 meters, exponential rule allows to reach 49 dB, followed by the exponential rule, and while max weight has shown its weaknesses again. Now let's move to the video over 5G flows. Using video over 5G streams, the SINR values are remarkably increased. The variation of the SINR as the user equipment moves away from G-Node is almost sinusoidal. Exponential rule is always the best algorithm, 78 dB at 60 meters. In second rank, the competitiveness of the PF and its variant, exponential PF, is well demonstrated, while the maximum weight values are criticized when comparing them with the other strategies. So to conclude, this work deals with scheduling. Scheduling algorithms in 5G networks. In the case of dense filter cells, for the match scenario, and in the the band above 24 gigahertz, the millimeter wave band, scheduling algorithms was implemented in C++ and tested in the millimeter wave model of industry simulator. We can see that exponential rule has demonstrated the best performance for the three types of flows: data, voice over 5G, and video over 5G. The PF and exponential PF offer compromise between the different quality of service parameters, system throughput and SINR, while max weight should be avoided for 5G networks regarding its demonstrated weaknesses. In the prospects of our work, we were planifying to implement other algorithms which have been done. Of course, this conference was planned before for April to be held in Marrakesh, but between that time and now, we have implemented other algorithms in millimeter wave model of industry, and we have submitted a paper on that. Then we are planning to simulate other scenarios with the mobility management, handover, and high-speed mobility. Thank you for your attention. If there is any question.
Thank you, Ismail, for respecting time. I think there is no questions on the chat. Karim, are you here? So we have one question. Ismail, you can read the question?
Okay, I'm looking.
So the question is about real time of traffic.
Presentation mentioned real-time traffic. Question concerns how we can verify this time constraints in your approach.
Yeah.
As you know, the 5G network was standardized before since 2016. And yesterday, in study group 5 of the ITU International Union, they approved a resolution about the different parameters and use cases of 5G networks, including the time constraints. There is, as I said before, three use cases for 5G, depending on which services the operator would like to implement. Each use cases have its time constraint. For example, for URLLC use case, it's defined as 0 milliseconds. So normally it's impossible, but theoretically it's possible, but practically it's not. We have tested also the delays of the different scheduling algorithms, but we haven't included that work in presented work. In our submitted paper, we have analyzed also the time constraints, what we call the delay or the latency, system latency, and we have verified that there, as it was the case for four algorithms presented here, some of the algorithms could reach good or low latencies, system latencies, but others not. I would like that our work, our submitted work, would be also accepted, and you can find more details about the system latency. Thank you.
Okay, Ismail, do you hear me, please?
Yes, I hear you.
Yeah, I have perhaps one or two questions for you. When we use simulation and to have a good idea about the final results, we should do more simulation. And I saw that you use only some parameters without changing them. Why? Because if you change the parameters, perhaps you will have others for the evaluation. You can have other results.
Yes, of course. Do you still see my screen?
Yes.
Okay. I would like to just confirm that, as you say, depending on the parameters, the results will be different. So that's why we have, as you say in the title, we have simulated just for the MMTC use case. MMTC is like an Internet of Things environment. We have implemented 100 user equipment just with the low speed, just to simulate MMTC 5G scenario, which include a dense area, big number of cities. Of course, when we will change the scenario, for example, increase the speed of the users, for example, include more service type, the results will be different.
Sure.
That's why in the prospects of our work, we would like to try to make three different use cases to be simulated in our work.
Yeah. Also the horizontal, the vertical handover is or are very challenges in this case in your field.
Yes, of course. One of the planned future work is to simulate the handover. We have done that in 4G because we have before trying to implement those algorithms in the 5G network. We have done for about 3 years our work in the LTE systems using other simulators. Now we would like to see. To study or to analyze how the system will respond when the handover is taken into consideration. Of course, that will be challenging because increasing the speed of the users will as a result will have a lot of handovers between different nodes. So that decrease the system performance. We would like to also study and analyze the handover algorithms for the mobility management other than radio resource management.
My last question. I don't know if you know. Yes, I mean, yes.
I think we have more presentations.
Okay, wait. Yeah.
But I think we need to respect time.
Yeah, okay, no problem. Ismail, will perhaps, if we have opportunity, we can exchange some question, some discussion between us. Yes, thank you so much, Ismail.
Thank you very much. Thank you.
Yeah, thank you so much. We move to the next presentation.
Abdulali Hadir is here. Abdulali Hadir. Any presenter for this paper? 96? No?
We'll move to the fourth.
Okay. Any presenter for paper ID 64? Rabi' Madani? Abdullah Idrisi? Abdurrahman Zahout? Nobody? I think we can back to Ismail and continue the discussion.
But I think, I don't know if Sbar has the recorder of the presentation of these papers.
I don't know the admin if he's recording or not.
Yeah, it should be. I don't.
We can do it, but
yeah,
up to the administrator to do that. So let's move to the last one. Maybe he's here. Or she's here. So paper ID 40.
Paper ID40 sent a message that they had a bad connection.
But
They want
connection.
to present it as a video. They want to present to a video, I think.
He has a video.
I think it can start. Then, if the quality is poor, we can move to the video presentation.
I don't know if they are present, but
I cannot see their message.
I can read their message. Dear colleagues, okay, they are here.
Yeah. Okay. Okay.
Dear colleagues, so I am from Plovdiv University in Bulgaria, and we will present our engineering approach for extension of the tourist guide knowledge base. The topic of dissemination of Bulgaria's cultural and historical heritage is part of the BEC project of the University of Plovdiv. Many electronic catalogs have been developed to present natural and cultural attractions and the folklore. Recently, using the results of our previous developments, we have been focusing our attention on creating a reference architecture known as Virtual Physical Space or VIPS that can be adapted to different domains including tourism. The Intelligent Tourist Guide as an Internet of Things application takes into account various factors such as the current location of the tourist, the free time available, the cultural, historical and natural sites in the region, etc. The implemented tourist guide uses a knowledge-based hierarchy of ontologies developed for different cultural and historical sites. The development of comprehensive ontologies is a so time-consuming task, and our idea to databases and to enhance the tourist guide knowledge base. Tourist guide uses a knowledge and restructuring of the tourist guide architecture. Database engineering will be in accordance with the CCO standard for the presentation of the cultural and historical sites and the UNESCO standard for natural sites. According to the definitions and normative documents of UNESCO and the accepted classifications, we develop our classification of the objects of cultural, historical, and natural heritage in Bulgaria. And we see in this slide this classification. The cultural heritage, they are developed by using of CCO standard, and the natural heritage for natural heritage, the CCO standard isn't usable. Cataloging cultural objects or CCO is a standard for data content that guides the choice of terms and defines the order, syntax, and forms in which data values should be entered into a data structure. CCO is specially designed for describing works of art, architecture, cultural artifacts, and so on, but CCO is not intended for natural heritage objects and collections. In recent years, our team has developed several software systems for processing information about Bulgarians' cultural and historical heritage and natural landscapes based on intelligent agents. For the digital presentation of Bulgarian cultural, historical, and natural heritage, More than 10 years ago, we developed the BEC, Bulgarian Electronic Cataloging Cultural Environment, which uses the CCO standard. We developed the BEC catalog according to this standard with the following components: work record authority, subject authority, concept authority, geographic place authority, personal and corporate name authority, and image record. In accordance with this architecture, numerous databases have been created. Databases with different natural objects have also been developed, but since the standard is not applicable to this group of objects, the structure of these databases depends on the type of the objects. For example, for lakes, caves, rock information, and so on. The virtual physical space or VIPS architecture is being developed as a cyber-physical social space ecosystem. A cyber-physical social space integrates various data from physical and virtual world and the social spaces throughout different technologies to provide human-readable abstractions and conclusions. In this aspect, the architecture of the VIPS contains basic elements as personal assistants that are implemented as a BDA agent, operative assistants that also are created as BDA agents, event engine, and guards that we use for integration between physical and virtual worlds, and two subspaces, the analytical subspace and the digital library subspace. The analytical subspace uses different concepts from the interval temporal logic and ambient-oriented modeling to manage space and time and events from physical to virtual world. The digital libraries contains various resources that are used as assistants in the space. According to the structure of VIPS, the digital library subspace consists of two parts: ontology network and the domain libraries. According to our goal, the ontologies can be organized into semantically associated hierarchies. An example of OntoNet architecture is CCHH OntoNet, or Cultural and Historical Heritage Ontology Network, developed for the tourist guide assistant. Ontologies are developed in accordance with the CCO standard. And in this slide, we see this meta ontology with different kind of ontologies and authority. The main goal of the tourist guide is to generate the routes, and we develop this touristic guide as a multi-agent system with some kind of the main agents. For example, questionnaire generation agent, or QGA, is an operative assistant that communicates with the user and collect his or her requirements by using the meta ontology. The second is knowledge generation assistant, or KGA, which is responsible for retrieving information from the meta ontology and then transmitting it to the personal assistant for visualization. Conclusive content aware ambient assistant generates a final route by completing the primary route with additional information such as the current location of the user, status of the expositions, working times, etc. And personal tourist guide presents the route and objects information to the user's mobile device using the information generated by the operative assistant. Our engineering approach includes the three steps. The first of them is to re-engineering existing database as creation of a new database structure in accordance with the classification of cultural and natural sites and the CCO standard, and transferring data from all databases to newly created ones. The second step is to change the architecture of the tourist guide in order to use the knowledge from the new database. And the third one is to change the methodology in CHH onto net to add information about culture and historical sites from the new created database. The database engineering regards a complete change in the data model that will be extended with the specific cultural and natural sites that will be included in under two main approaches. For all cultural and historical sites, we will use the CCO standard, and to describe natural objects we'll create a similar database structure in which, depending to their type, natural objects will be described in the same manner as the CCO standard. The second task is to change the architecture of the tourist guide in order to use the new database. We suggest to add two elements to it: a CHH database and a knowledge generated agent database. The third task is to change the methodology in CHH onto net. Information will be added from a new database, CHH database. In this way, the questionnaire generation agent will be able to send a request to the knowledge generation agent DB about objects of interest. And we see in the right this communication with the knowledge generation agent DB, with the CHH database, and the tourist guide assistant, and the question generation agent. Let a tourist is located in the small town Madan in Bulgaria. After conducting a survey with the tourist to clarify his or her interest and desires, the tourist guide offers the user a list of the sites to visit and the suitable route. And we see the whole scenario and communication between the main agents and the user. Scenario. According to the current scenario, the question generation agent communicates with the tourist guide assistant and conducts a survey with the user by using her or his mobile device to determine his time available and his or her desires. And this is the screenshots from this communication. According to tourist wishes, the question generation agent sends regards to the knowledge generation agent and knowledge generation agent DB to search information from the ontologies in the meta ontology CHH onto net or in CHH database respectively. After receiving the result, the question generation agent passes this list of the object to the tourist guide, which sends it to the tourist for an additional choice. After selecting the list is sent to the CCAA agent, which throughout communication with the guard system in dynamic mode receives information about the objects, museums, expositions, and so on. CCHAA then submits the information to the ABNet environment where tourist route is generated in simulation mode. If the tourist wants to take a real or virtual tour, his or her personal assistant displays the necessary information and provides assistance. And we see some screenshot from the mobile application. And in conclusion, we see that VIPS as a cyber-physical social space ecosystem can adapt to different domains for tourism, smart agriculture, smart city, learning and others. The tourist guide assesses VIPS adaptation regards the development of additional components that extend and enrich the basic VIPS architecture. The discussed approach allows us to extend of the knowledge base with cultural, historical, and natural sites. In the future, we'll extend the CHH onto net meta-ontology with a new ontologies, which will lead to problems related to the duplication of cultural and historical sites in CHH onto net and CHH database.
We thank the presenter, and she asked us. She has a problem or the connection problem, and she asked all the audience, if you have please question, you can ask your question directly by email to her or to them, to all the authors. And now we move to the next presentation. I don't know, from Abdurrahim Zahoud. We have, I don't know if we have the stream. Yes, Rabi Madani. I don't know. You sent. I think you sent your video, your stream. Yeah, you are online. You can do your presentation. Please go ahead. Rabi, you can share your you can share your screen, your presentation, please.
Maybe we can move to Abdulali Hadir. He's here. Maybe. Mr. Hadir, do you hear me?
Hello
everybody, I'm Madani.
Yeah, Rabi, oui, Rabi. Yeah, Rabi. Okay.
Science in Rabat. Today I will talk to you about an overview of recommender systems in the context of smart cities. Here is the content of my presentation. So, Internet of Things represent a system of interconnected devices in order to collect, process, and store data. It became a very important factor that influences our lives. It can be applied in several domains such as healthcare, agriculture, retail, smart homes, and smart cities. The concept of a smart city appeared to face urban problems and to improve quality and efficiency of services. However, this large number of services can cause problems to users and make the choice of the needed service very difficult. Recommender systems solve this problem by helping users in selecting services and products based on their preferences. The figure below shows the steps to provide recommendation for users, beginning from data collecting, passing by data processing, and ending with providing recommendation to the end user. The purpose of this paper is to provide an overview of existing applications of recommender system technologies in smart cities, also to discuss challenges and open issues researchers can work on. What is a recommender system? Recommender system is a class of information filtering systems which provide recommendations to users based on their preferences and behavior by exploiting several strategies. We distinguish 5 techniques of recommender systems: content-based, collaborative filtering, context-aware, knowledge-based, and hybrid recommender system. Content-based filtering is based on item descriptions and users' profiles to generate recommendation. Both are represented as weighted term vectors. The basic process used by this approach is to suggest items to users that match with their preferences based on similarity. Content-based approach use sample retrieval techniques such as the vector space model. The content-based recommender system have several drawbacks such as the over-specialization, which occurs when the system recommends only items similar to those rated by the user. The new user problem is another drawback of content-based because users should rate a sufficient set of items before the system can really provide recommendation for them. In contrast to content-based, collaborative filtering doesn't need content information. This technique is based on rating information to produce recommendation. The rating is divided into 2 categories. Explicit rating is the rate given by users to item directly, for example 5 stars rating or like dislike an item. Implicit rating is based on users' actions on specific items such as clicking, saving, bookmarking. Besides sparsity and scalability challenges, collaborative filtering approaches have other challenges like cold start problem, which happen when dealing with new users or items or due to the lack of information. In these cases, it is very difficult to provide good recommendations. Collaborative filtering and content-based recommender systems provide recommendation based on 2 entities, users and items. However, these approaches do not put the recommendation into a context. In fact, contextual information such as position and time could be very useful and bring more predictive power to the recommendation. The idea behind context-aware recommender systems is to incorporate the context when providing recommendation in order to increase the prediction accuracy. Knowledge-based recommender system is a particular type of recommender that rely on explicit user requirement and knowledge about product domain to provide recommendation. This type of recommenders is well suited when content-based and collaborative filtering could not be applied. For example, in the case of complex items such as financial services, cars, computers, or houses, where a deep knowledge about product domain is needed. Knowledge-based recommender systems requires a big effort in terms of knowledge extraction, representation, and system design. A knowledge-based system uses a variety of techniques, so it's a complex approach. Hybrid recommender system combines 2 or more recommendation techniques in order to avoid some weaknesses and benefit from strengths of any one of them. Since the 1990s, many works and applications of recommender system have been proposed in several domains such as e-commerce, music, video, and others. The recommender system have gained popularity thanks to the benefit they bring to businesses. Nowadays, the majority of e-commerce websites use recommender systems to help customers to find products that satisfy their needs. Amazon, for instance, use item-to-item collaborative function to personalize the store for each customer. Music and video are inactive areas of research, especially with the fast growth of these kind of resources. Many music recommender systems have been developed, such as Flycast, which generate a playlist that matches the musical preferences of listeners. Regarding the video areas, the recommender system of YouTube is based on deep learning, artificial intelligence, and comprised of two neural networks. The first collects users' information and activity history using collaborative filtering. The second one ranks the selected videos by assigning a score to each video. The top scored videos are suggested to users. In last years, many applications of recommender system in smart cities have been presented. For instance, DiMartino and Rossi proposed an architecture for mobility recommender systems which provides door-to-door routes by exploiting data from many sources such as digital maps, parking information, and user preferences. The system provides for each route requested a list of potential door-to-door routes, the estimated time of arrival, and operational information about public transportation to be used to reach the destination. The proposed model has many limitations because the generated recommendations are based on a lot of static data which are not updated in real time. Consequently, it impacts the quality of recommendation. Jimenez and Bravo presented a multi-agent recommender system aimed to optimize and reduce electricity consumption. The system is a standalone knowledge-based and utility-based recommender system to provide a recommendation by exporting consumption information generated by smart devices and electric price from internet. However, the system has only been tested in a theoretical case study. Kumar and other researchers proposed healthcare recommender system which suggests healthy routes to users based on their health information and real-time data collected by smart city infrastructure such as air quality, temperature, ultraviolet radiation, and wind speed. The communication infrastructure integrates a variety of wireless technologies that can be also enhanced by location services. There is no need for a complete set of electronic health record. A general overview of the user's health condition is enough for this model. Recommender system in particular and smart cities in general meet several challenges. These challenges are described below. Data processing short period of time in different data types. This challenge is considered as a big data challenge and need to be addressed by adopting a global strategy that aims to collect, organize, and process and also to verify the quality and reliability of the data. The engagement of community is another challenge facing common systems in smart cities. As a matter of fact, for smart cities, smart citizens are an important part of the system, and they should be engaged in all aspects, starting from data collection to the deployment of the solution, and finally by giving feedbacks to evaluate and improve the quality of services. It is essential that community feels like it's an integral part of the whole system and the decision making. Privacy is another challenge and have a direct impact on the engagement of community. The enormous number of sensors and cameras installed throughout the city, in streets, in bus stations, in parkings, and also in smart homes make people feel like they are being spied by the government, and their privacy and personal life is in danger. This issue could have a negative effect on data collection and can also engender a problem of mistrust between people and authorities. To address the problem of trust, government and lawmakers must adopt privacy laws and policies which regulating the use of personal information of individuals and increase transparency. Conclusion. In this work, we have provided an overview of the use of recommendation approaches in the context of smart cities. First, we have given a short description of recommender systems, types of recommender systems, and basic application of recommender systems. Thereafter, we have shown how basic recommendation algorithms can be applied in smart cities. Moreover, we have discussed or described the challenges facing recommender systems in smart cities. Thank you for your attention.
Thank you, Abdurrahman, for your nice presentation. Do you hear me, please? Do you hear me, please? Abdurrahman, do you hear me, please?
Abdurrahman, your mic, please. Your mic.
This is Rabi'. Donc Rabi'. Ah. Excuse me, this is Rabi'. And I have course and I am.
Karim, I think nobody from this paper can answer. They are not.
Yeah, I think.
Yeah,
I think.
Yeah. The next presentation.
I don't know if Abdel Hadid is here or not.
His name is here.
I'm here. Hadid, you are
Hello,
here.
Professor. Hello,
you
Professor.
are here. Yeah. Yes, please go. Yeah, please go ahead, please.
So, hello, Professor Amin. Hello.
Yes.
Hello, Abdulali.
So I just share connection from my phone, and it's not stable. Sometimes it's cutting. I sent you my presentation yesterday. So.
Yeah.
If you don't have any problem, please, we can, you can, could you please use my video presentation recording?
Yeah, we don't have access to your presentation.
Exactly.
Maybe the admin can do that.
Yeah.
Okay. So I will try to
Yeah, we see. Yeah, we see you very well. You can go
Okay.
ahead. No problem.
So can I share the screen with you, Professor?
Yes.
Yeah.
Oh, okay.
Okay, you can stop the video and share the presentation.
Hadir. We don't hear your presentation. Please open your mic. Hadir, please, we don't hear you. We didn't hear your presentation. Hadir, do you hear me? Hadir? Hadir, please. Hadir? Hadir, do you hear me? Hadir? I think Hadir has a big problem in his presentation. We don't hear him. And I don't know if Hadir. Hadir. Sorry for the audience, we have a problem. Hadir has a big problem in his presentation. And if he can't continue his presentation, we are going to finish this session. Hadir? Hadir? Yes. Unfortunately, he has been disconnected. And sorry for the audience. Thank you so much for being with us this morning for this session. And thank you so much. I'm telling you, we stopped this session because we are in the end of the session. Unfortunately, we can't continue. Some presenter have some problems, and I wish you a good conference and stay safe, and see you this afternoon. Now we stop we end this session. Okay, you are welcome. You're welcome. You're welcome.